All right, now we're going to talk about the last bit of chapter 1, and that has to do with a number of little different topics. One is we're going to use the Greek alphabet a lot. We'll be using it because we don't, if we used X for everything, physics would be so confusing. If we use the same symbol over and over and over again, and even then, we'll use T for time, we'll use T for temperature, we'll use T for tension. So even with that, we're still going to have some repeated use of some of our alphabet. All right, so in physics, we use the Greek alphabet a lot simply to help us keep things straight and keep things clear. Now, some of you may know some of the capital letters in the alphabet, like pi, kappa, alpha, but you're less familiar with, well, pi you know, right? You're less familiar with the little kappa and the little alpha or beta or gamma, right? So the lowercase Greek letters, for the most part, you're completely unfamiliar with. Some, but not all, of the uppercase Greek letters are you familiar with. So just be aware. We're going to be using these. When you see one of these, don't get confused. Don't get confused. Just accept, okay, this is a Greek letter. I need to make sure I understand what meaning we're assigning to it right now. And that's the important part. We'll use alpha for angular acceleration. We'll use theta for angle all the time. We'll use omega for angular velocity. Omega down here, angular velocity. Lambda for wavelength. So there are Greek letters throughout all of this that we'll use again and again and again. On circles, spheres, things you'll need to have just at the top of your mind all the time. What is the circumference of a circle, right? 2 pi r. What is the area of a circle? Pi r squared, right? Where r is the radius. Or pi d squared over 4. What is the area of a sphere? The surface area of a sphere, radius r, 4 pi r squared. What is the volume of a sphere? 4/3 pi r cubed. So all of these you just need to have in your head. They're in table C9. They're in this appendix C of the book. So if you forget about it, go back. Make sure that anytime we're dealing with anything in the chapter, in a chapter that deals with circles or spheres, that you have these in mind, because these are pieces you need to know. Now, a little bit difference between accuracy and precision. All right. So if you look at this and versus this, in the top diagram, the marksman in the top target was more accurate. More accurate in that if you look at where the average position of all of these is, it's closer to the middle of the bullseye. This marksman was more precise. All right. This is more precise. So accuracy is how close your average is. Precision is how tight your grouping is. So those are two different things, right? Two different things. But we need to keep them in mind on occasion. An accurate prediction versus a precise prediction, they don't mean the same thing. Significant figures. Because of calculators, often you will carry out way too many significant figures, and you'll give me an answer that's like 3.1415927 when I only really needed like 3.1. Why? Well, here I have 1.0 times pi. Now pi, you know, has an infinite number of digits. You're never going to write those down. I don't even want you to write the first 100 down. But the 1.0 only has 2 significant digits. So when you get down to the end, 3.1 is all we can say about this, right? 2 significant digits. Here we have 14.389 plus 5.6. We have 2 significant digits here. I should probably just write this as 20, right? but I took it to 20.0 because we have a significant digit in the 0.1 place on both of these. So we have 20 as the answer, not 19.989. If I wrote this as 5.600, then 19.989 would be the correct answer. But I didn't write it as that. I wrote it as just 5.6. Approximations. So a lot of times you will see me up at the front of the class when we're solving problems during class, and I'll do approximations to try and get to the answer without having to use a calculator. All right, do this all the time. Um, we do approximations. Physicists, real physicists, do approximations all the time when they're just trying to work through something and they don't have at hand a good calculator. Knowing how to do what I call napkin math is a really good skill, because napkin math will let you quickly get to an answer sometimes that gives you the neighborhood that the answer is going to be in. It's approximately correct. Napkin math is just important in terms of just understanding the world around us in a quick way, making sure that the numbers we're talking about kind of make sense. So approximations, being able to take things not quite so seriously, calling pi 3, calling the acceleration of gravity instead of 9.8, calling it 10, working through the problem with those numbers to get to something resembling a solution. Being able to do that is going to be important at different points in your life. Finally, the math we're going to use in this class. It's algebra, right? It's algebra. And some trigonometry, but pretty simple trigonometry. We're not going into esoteric trigonometry. We're not pushing the envelope on trig. We're using the very basics from trigonometry. So we'll be using algebra, we'll be using trig. I'll do my best to make sure we go over the trig every chance we're going to run across it, or every time we introduce it, and we will figure out what we're doing with the trig as we go. All right, that's the end of chapter 1.